Hello everyone. I'm presenting the paper Prospective Time Periodical Geographical Disease Surveillance using a scan statistics. That's such a long name. The author of this paper is Martin Kaldoff, and I'm the presenter, Dongdong Lu. So before we talk about statistics, let's first look about the popular culture. I believe many of you have ever watched this TV show. It's called Breaking Bad episode 1, Cancer Man. So in that TV show, this gentleman, White, was working for Los Alamos National Laboratory 20 years ago as a technician. However, 20 years later, he was diagnosed of lung cancer. And that's where the whole story begins. The story happens in New Mexico, and luckily, in this paper, we are going to talk about the cancer rate in New Mexico also. Introduction. So traditional space-time disease clustering method, they are retrospective in nature. However, in this paper, the author proposes a method that is prospective in nature. And it is based on space-time scan statistics, which may still be unfamiliar with you. However, we will see how we define it in a few slides. It only detect those clusters which are still alive, which means those clusters live to the current time point or to a time point where the data is connected, the end of data connection. It can detect the cluster irrespective of its age. And multiple useful adjustments can be made about its statistical inference. The author is trying to implement his new method on a dataset. This dataset is about male thyroid incidence data from New Mexico. And it was connected by the National Cancer Institute. And some of you may know that New Mexico has 32 counties. In this dataset, we totally have 333 cases. The incidence rate is very low, with only 2.4 per 100,000. The denominator, in particular, the denominator in the scan statistic is age-specific population estimates for each individual year for each county. Before we see the mathematical formula for the scan statistics, let's first look at this New Mexico map. And notice that I put a few stars on this map. Those stars are the centroids of those geographic area of those counties. And I also put 2 circles on it, which means we're randomly taking points from this map. If this circle contains those centroids of the counties, then those counties are merged together. They were put under one study for the clustering. The circle we had in the previous map, it can be small, it can be big. However, it can never include more than 50% of the total population at risk. As you can see, as the circle travels around the map, it can connect nearby counties into one study. Here, you can see the formula we define our scan statistic. Here, capital S is a scan statistic. And it basically is just a maximum of the likelihood ratio. The Numerator of that ratio is the maximum likelihood for the circle, the area covered by the circle. That means how likely the observed data are giving a differential rate of events within and outside the zone. The L0 is a likelihood function under null hypothesis. The null hypothesis basically said that the disease happens randomly across space and time. And small nz here is the number of cases inside the circle. Capital N denotes the total observed number of cases. For the Poisson model, we use mu z to denote the expected number under null hypothesis, which means how many cases do you expect if everything is purely random across space and across time. And as this likelihood ratio is maximized over all circles, and those circles are moving and covers different counties, this scan statistic can identify those circles which constitutes the most likely cluster. As for the p-values, it can be obtained by Monte Carlo hypothesis testing. Basically, we're just using the null hypothesis to see how extreme the statistic can be if the null hypothesis is true. This scan statistic has certain properties. It adjusts for inhomogeneous population density for any number of the confounding variables. It can search for any cluster irregardless of the size or location. And the likelihood ratio takes multiple testing into account and delivers a single p-value. Finally, if the null hypothesis is rejected, we can specify the approximate location of the cluster. If we use the scan statistics for purely spatial analysis, from the time period 1973 to 1978, the most likely cluster happened in Bernardino and Valencia counties, but the p-value only has 0.44, which is so large that is not significant. So here comes the first problem of pure spatial analysis. It has no power to detect emerging clusters. And in the counties we just mentioned, 46 cases were observed, while 34.6 are expected. However, the p-value is 0.44, as we just mentioned. So we conclude that for that time period, there's no evidence for geographical differential risk. And basically, this paper confused me at this point. So here comes my question number one. So why does the author choose this part of the data, 1973 to 1978, to do the purely spatial analysis? The proposed method, as we will show later, didn't show any unusual about it either. So purely spatial analysis and spatial time scans statistics, they basically give the same result, which is no significant finding for this time period. So what is the point of single this piece out? I hope you can answer my question. So this is one point which confused me. Then the author applied this purely spatial analysis on the whole dataset. He made such a table. Notice that in this table, for the last 5 rows, they are statistically significant. And those areas are north central counties, minus one of the county inside those north central counties, or plus a county which is outside those counties. The p-values here are not adjusted for repeated time periodical analysis. And as we will see in the next slide, the author will discuss the weakness of such a purely spatial analysis. So firstly, we have a low power of detecting emerging clusters quickly. If a true excessive excess risk only presented during the last few years, then if we are doing a purely spatial analysis for the whole time period, we will dilute the strength of the clustering by random fluctuations of the rate or for the early years when the risk is not high. The second weakness is that while we are adjusting for multiple testing, stemming from many possible cluster locations or cluster sizes, we're not adjusting for the multiple testing due to the repeated analysis every year. For example, if you look at the 15 analyses done in table 1, some of them are significant. However, others are not, making it difficult to interpret the result. So we just look at the previous table. And as you may notice that on the previous table, it mentions relative risks. So here comes my second question while reading the paper. And this question has been answered by Mohammed for me. It is just observed number of cases divided by the expected number of cases. If you observe, let's say, 10,000 COVID cases in Denver, however, you only expect 100 cases in Denver during this time period. So the relative risk for Denver in this case is 10. And here comes to our next section. We are detecting emerging clusters. In other words, we are incorporating the time information. I hope you guys still remember the circles are made on the graph. That's imagine a cylinder. The circles we made on the map were just the bottom of the cylinder, which has information about space. However, in this new section, we're also introducing the time, so which is the third dimension for the cylinder. We consider all the possible starting date for the cluster or location. And we only care about alive clusters, which means we only look at the data from the any beginning point to the end point when the data is connected. So let's say this year is 2020. If the data is only collected in the year 2020, we only consider those cylinders to 2020. Okay, if you have the data, the end year is 1998, then the cylinder time only ends at 1998. That's the time period you consider. Again, the likelihood ratio test statistics is done in a very similar way using the same equation. The p-values are also get by the same method. We randomly distribute cases across space and time. And this time, since we're working in the 3 dimension, it becomes a little bit more computational expensive. And the most likely cluster will remain the same, but the p-value will be a little bit higher. Okay, so once we have this new space-time scan statistics, let's implement it. And the author gets the following result in the implementation. Basically, all the previously significant cluster disappears. Only one with only one left. That is Los Alamos cluster. Here, he listed those most significant clusters. And as you can see, the p-value for most of them are just too large to be significant until you reach end of the table and you see the Los Alamos County. Let's walk through this table a little bit from the year 1973 to 1978, which is still the same most likely cluster, Bernardino counties, and the p-value is 0.6, which is too large. In 1985, the algorithm found that Lincoln County has appears to be a cluster, but not confirmed yet. It has a relatively risk of 13.8. But the next year, when you add the new data, which is no confirmed cases in Lincoln County, it was no longer the most likely cluster in that year. So the previous cluster was perhaps just due to a probability of chance. Then it comes to the year 1991. We suddenly have a statistically significant cluster. And the p-value is 0.02. However, with the next year, another 2 new confirmed cases were added into the dataset. This brings the p-value down to 0.002. This county, Los Alamos, has totally 9 cases, while we only expect 1.2 cases. So basically, this is the only statistically significant cluster. Then, in the section 5 of that paper, the authors start to make a little bit modification on how we calculate the likelihood ratio and came up with this time periodical surveillance. The motivation was pretty simple, that new cases were added to the disease data every year, and we need to reanalyze them every year. Still, we are interested in the alive clusters. However, while calculating for the random datasets or for the null hypothesis, this is a difference. The likelihood is maximized over all cylinders. in addition to the current cylinders. Or in mathematically, we have another t greater or equal to ym. Ym means the year which the time periodic of surveillance begin. We have this new term while calculating the likelihood ratio. And notice that there's another formula recorded on this slide. That is y1 smaller or equal to s, smaller or equal to t, smaller or equal to y2. This s and t, this t is not fixed at y2. So both s and t can moving along the time axis, which means it is considering all possible time intervals on this dataset while calculating the likelihood ratio. Here comes my third question about this paper. While reading this paper, I noticed that there was such a long sentence which I do not fully understand. I'm not going to read it word by word, but during our Friday's discussion, please give me some insights on how we should understand this long sentence. Okay, once we apply the new updated version of the space-time scan statistics, the author gets such a result. Notice that all other rules are still the same with the previous table. The only difference are listed in this table here. That is, from the year 1973 to 1991, that cluster was no longer significant. Recall how we calculate about the likelihood ratio in the new version of statistics. We maximize all possible on the null likelihood on all possible time space, which makes the denominator of the ratio bigger. So the overall fraction is kind of getting smaller. So that's why what was previously significant now after this update becomes less significant. However, if we added the data of the year 1992, we found this cluster become again significant with a p-value 0.016. Let's look at this graph. This graph shows that the expected cases in Los Alamos County and actual observed number of cases. As you can see, from everything still looks normal from the year 1973 to the year 1989. Then that year, we see 4 new confirmed cases, which significantly increased the risk ratio. However, by that time point, it's not significant yet. Then we come to the year 1991. So with new cases confirming, the risk is getting bigger. However, still not significant until you reach the year 1992. And that's where you get a p-value smaller than 0.05. And it officially become a significant cluster. So the final section of that paper was discussing all different details and aspects of his method and other people's method. He mentions that his method considers all cylinders of possible temporal lengths, but only up to some pre-specified maximum. And this pre-specified maximum can be a couple of days or a few years. It really depends on the disease. For example, as we all know, the latency period for flu is very short, a couple of days, a week at most. However, the latency period for cancer can be very long. Someone can get contaminated with bad chemicals or receive too much radiation. Then they can be diagnosed of cancer decades later. So that's a point which you need to, the disease, the type of the disease you are studying on it really affects this specified maximum. And they also do not recommend you to have a strict cutoff for the p-value. He emphasized that, and I agree that p-value only serves as an indicator concerning the evidence for a real cluster. So if this p-value is small or it is significant, it just means the evidence is strong. If it is strong enough, a detailed epidemiology study with individual case history should be conducted. And as always, we have background rate. So cancer almost always happens in every county, no matter how the good environment is there or bad environment is there. And his method cannot detect historical clusters that begin or ended before the time which the surveillance began. He also briefly mentions the difference with other prospective geographical surveillance system, that he emphasized that his method can detect specified geographic locations. And other methods is more designed toward detecting a certain appearance of cluster as a global phenomenon throughout the geographic area. So in other words, he thinks other methods are less likely less able to determine the exact location of the cluster. Finally, he points out the latency period of the disease plays a very important role. That is, for long latency disease, even all the exposure were remote, new cases may continue to occur. And the follow-up, monitoring, and evaluation will be very necessary. So this is the end of the paper here. So let's go back to the TV show Breaking Bad. As I just mentioned, the long latency period plays a role in the study. So the main character, Walter, in that TV show, he was exposed back in the 1980s, and he was diagnosed cancer more than 2 decades later. According to the author's last suggestion, all of Walter's previous co-workers in the Los Alamos laboratory should be on regular medical checkups. That's it for this presentation. Thank you very much for watching. Please let me know if you have any questions. And also please consider my questions. And if you have an answer, please do not hesitate to tell me on our Friday's discussion. Thank you. Goodbye.